a great pleasure to have you. Thank you for coming, and please go ahead.
Thanks, Martin. I'm pleased to be here and to meet many of my old friends and also meet new ones. So I'll be talking about representing text in context. And let me start with some background and talk about what does it mean to represent text and why do we need that, starting with some early work. In order to build a machine learning model from text, for example, if we want to classify movie reviews, we need to first represent the words with vectors. And traditionally, words in early models were represented with one-hot vectors. And those are just large vectors that for every word, they would have a 1 in one place and 0 anywhere else to indicate the word. Using this representation tells the model that any two words have the same similarity, which is 0. And the model doesn't know, for example, that king is more similar to queen than to apple, and has to learn everything about the task from a small training set. Oops. So, John Firth, who was a famous linguist, said that we can know whether words are similar by their context, by the company they keep. So we can know a word by the company it keeps. And this insight has led to the idea to start learning vectors for words based on their occurrences in unlabeled text, for example, web articles or books. As an example, for both king and queen, we can see a phrase like this, which both of them appear in the same context, which can help us learn that those two words are similar. And there was a lot of work on building vectors for words from large texts. And those vectors indicate similarity of words in different aspects, and they've been really useful so the models can start with some knowledge about the words. So that was about 8 to 10 years ago. So this is a big improvement. However, we know that words in different contexts have different meaning. For example, the word bank in the phrase open a bank account means something different from bank on the river bank. And ideally, when we have our machine learning model, we would be able to tell it that the vectors of these words should be different in the different contexts, and also tell it how they should be different. In other words, we want something that sits on top of the word embeddings and tell us how to make different vectors depending on the context. So there has been a lot of work on building such representations from context, and it turns out we can use the same insight to do that. We can learn neural networks that give contextual representations of words just based on words appearing in unlabeled text. For example, we can train a contextual encoder of a neural network, for example, a transformer, to learn to predict the next word given the previous words in a sentence from large data. So turns out this is very powerful, and we can learn to build a vector for every word based on the context on the left with a deep neural network. And it's learning to represent the meaning in the context. there was models like Elmo and GPT-3 that show that we can improve performance on some core tasks quite substantially by using these representations from unlabeled text. So then comes in BERT, which Martin mentioned, where we build on this work to make a small change that turns out to be very powerful, which is that we can learn more flexible representations of the context that take into account both left and right context, and they can be used for many tasks directly. Now, we cannot learn how to contextualize both from left and right using a left-to-right language model, but doing a simple change, which is to take sentences out on the web and mask out some words in the middle and predict the words in the middle given the context. In this way, we can learn to take into account context from both sides and use our neural network as the contextual encoder. If you have a very flexible neural network that represents deep vectors for every word in context, it turns out the ML model on top for our task, it doesn't need to do a lot. We don't need a lot of new parameters, and we can rely a lot on this knowledge learned from unlabeled text. So given a pre-trained model, we can use it for tasks like question answering by extracting answer spans, and we can use it for many other tasks. And this change resulted in very strong empirical gains across many tasks, maybe gains we hadn't seen in periods of 5 years before that. So far, by now, representing text in passage-level context has become pretty standard in NLP because it's a really powerful way to compute the meaning representation. In the rest of the talk, I'll be giving examples, other work, where we look at cases where it's useful to consider context beyond a single passage. One type of problem is where a single passage may not be enough to disambiguate, to really represent the meaning. And another case is where maybe we can disambiguate, but in order for the model to integrate all the background knowledge we need for that, it needs to be very big. To give you a sense of how language models learn to represent background knowledge, we can look at an example like this in unlabeled text. We paid 20 blank at the Buckingham Palace gift shop. And neural network is trying to predict what goes in the blank, in this case, pounds. And in order to figure out the word pounds needs to go in there, it not only needs to know it has to be type of currency, but also that Buckingham Palace is in the UK and it uses the pound. So in order for models to integrate this type of very fine-grained knowledge, they have to be very large, which is expensive. So I'll be talking about 3 different ways in which we can integrate context for better accuracy. First is to integrate background knowledge explicitly through context instead of model parameters. And the second are where we really need to use the context to disambiguate. In this work, the paper at the bottom, this is recent work, we looked at the problem of question answering from documents. Standard models will read passages and build up representations from the passages, but we often need a lot of background knowledge. In this work, we retrieve textual encyclopedic knowledge about entities mentioned in the passage, and we integrate those explicitly as text to build more knowledgeable representations. And a standard approach for question answering would take a document and read it in chunks, for example, of 512. They have to be chunked because otherwise it's very expensive. And compute representation of each slice, and then compute probabilities for answers at each position. In this work, what we do instead is we process shorter chunks of text, but we concatenate sentences about the entities mentioned in that text and encode that knowledge together with the text. We call this enriched representations. And you can use any pre-trained model with this new context, and it would work fine. However, we show that if a model is pre-trained in a way to take into account the entities that it knows it will be integrating information from many pages about entities, it can work better. So we design a specific pre-training task for that and pre-train the model to integrate the knowledge. This has given some strong improvements on knowledge-intensive tasks, and this is an example on a trivia QA task. Next, let's look at representing tables. Tables are interesting. They do have text in them, but in addition to that, they have structure, which comes from the columns and rows. In order to build representations for tables, in this paper listed at the bottom, we design a graph neural network that can attend on the structure and integrate it better. And we show that pre-training this model is better than just taking an off-the-shelf model. Even if we have a pre-trained representation on tables, it's still insufficient to disambiguate. Let's look at, for example, the question, what are the most popular individual sports posed for that table? If we just look at the table, we cannot tell which row talks about the most popular sports. In this paper, we had the insight that many tables appear in articles, in documents, and we can search for facts that talk about the table and help us disambiguate. And this is what we did. In this example, we can see that there's one sentence saying, category A represents the most popular sports, and together with the table, this can help us answer the question. So we integrate that context, and we show improvement on the task of real question answering on tables. And last, I'll talk about visual context. There are many domains where we see a visually situated text. Some examples are diagrams, and students on science questions, science exams would see something like that, asking what the diagram depicts. Another is app screens, for which we want to have a description of what the app does. And we can see both text and visual elements on it. Another example is graphs, diagrams, where there is text, but also other elements that show the information. And a final example is signs or information boards in real life that we can see. So most work that is on this area tries to separate the visual elements from the text elements, because we know how to do vision, we know how to do text. I mean, at least there is a long line of work. And then try to, let's say, run optical character recognition on the images, and then encode with our text encoder, the vision encoder, and then do the inference, joint inference at the later stage. However, separating these modalities out with something like OCR may lead to errors, because it may, if we make an error on the recognition, then we may not be able to fix it. So research so far in these different domains of visually situated text has been fragmented with people building domain-specific solutions. In a recent paper, we are asking, can we just build a model from the pixels that can jointly understand the text and the visual elements and be able to answer questions, generate text, and do all of these tasks from the variety of domains. In this recent paper, we pre-trained such a model that represents the image that can have a lot of text and converts it into a text, which is a structured representation of the image. In particular, we use screenshots of web pages, and they have a lot of text in them. They also have images. And the model is trained to generate a HTML, simplified HTML of the image, which will tell us what are the words in the image, and also gives us cues about the grouping of the elements, the hierarchical structure, and also there are signals from captioning. For example, there is alt text, Belgian buns, that tells us there are buns in this image. So we pre-trained this model from pixels only, and we are curious how far it can go without OCR, with fine-tuned on all the different domains. This is data sets from these different 4 domains, and we compare first to other work that doesn't use pipelines or external information, doesn't use OCR. And our model is called Pix2Struct. And here we can see that in all of the data sets, except for image captioning on text caps, our model does better. So the text caps domain is this domain of the natural images, and the model that does better, called Git2, is pre-trained on 150 times more data and is 5 times bigger. So we may think that our approach may also get there, but this other model is only working well on the image, natural image domain. If we compare with any model out there that's published on dataset, including running OCR and building text and image representations, we see here that that Pix2Struct does better than the models on the most tasks, except for document QA and info VQA, which are the 2 on the right. And those tasks are very heavy on text. They have long texts. And in this case, the pixel-only model has a disadvantage. So in summary, what I've shown here is that we can learn how to represent text in context from unlabeled text, and that those models are really useful. They've been improving the state-of-the-art quite substantially in recent years. Also that there are ways to use additional context, both from background knowledge and multiple modalities, to build better representations. Looking ahead, there is more we can do with larger models and longer context, larger data sets, and there will be progress there. but each of those directions leads to increase in computational complexity. So computational efficiency of these models is emerging as a very important area, as well as fragmentation of different models that are trying to represent different contexts. So I think this is important areas of work. That concludes my talk. Thank you. And these are my collaborators.